Okay.
And let's begin. So, ideas. First one. What you guys try?
Double angle and then expanding.
Okay. What does it look like?
It should be 1 minus cosine 2x squared times 1 plus cosine 2x.
So 1/2.
Sorry, yeah.
2x squared times 1 plus. Well, there's going to be another half.
Yeah, so it should be a total of 1/8.
The squared here, so that's 1/8, and that's 1 plus cosine 2x. Okay, then?
Then you expand everything out, and I believe that should be 1 minus cosine 2x minus cosine 2x squared plus cosine 2x cubed. That's after doing everything.
Yeah, I don't know if I want to expand a triple one. Let's apply the difference of squares first. And expand these. So 1 minus cosine 2. No, I already used them. So I thought of this as, of course, this is 1 minus cosine 2x times 1 minus cosine 2x, right? And this one times that is a difference of squares, so I got this. And then this one is this one left over. So now I want to expand this. 1 times everyone over here, I get that. And this times everyone over there, so I get minus cosine squared 2x and plus cosine cubed 2x. With me so far, you got that line? Who was actually? Oh, yeah, did you get?
Yeah, I basically just gave that whole thing. I
Okay.
skipped the middle step.
Okay, so now what? What did you do from here?
So I just redistributed the integral to each of the term, and then just integrated whichever I could. So the first two you should be able to integrate. So
Right, so this is 1/8. Now, of course, this one here, you can apply the double angle
Correct.
formula again. This is actually going to be minus 1/2 1 plus cosine 4x, right?
Yep.
And so integral of 1, that's going to be x. Integral of this, that's 1/2 sine 2x. Integral of this, well, that's just going to be minus x over 2. Integral of that, that's going to be minus 1/4 sine 4x. How did you deal with the integral of this?
So I took out cosine 2x squared. So then you should have cosine squared 2x times cosine, and then substitute in 1 minus sine squared of 2x.
Right, so, because this now brings you to that case where we're dealing with an odd thing. Right?
Correct.
So we already had the formulas for those. So this is going to be, I can take the x minus the x over 2, so that's just x over 2 minus the 1/2 sine 2x minus the 1/4 sine 4x. And then here, it's going to be the 1/8 times 1 minus sine squared 2x times cosine 2x. So just think of this as cosine squared times cosine. Change the cosine squared into 1 minus sine squared. And of course, a substitution here is going to do that. du is going to be minus 1/2 thing of integrals 2 cosine 2x dx. So this guy is going to become, you're going to get 1/2, so it's going to be 1/16 times integral of 1 minus u squared du. u minus u cubed over 3. I guess at this point, let's just copy everybody back. So it's going to be 1/8 x over 2 minus 1/2 sine 2x minus 1/4 sine 4x plus sine 2x over 16 minus sine cube 2x over, what's 3 times 16? 48. You guys get the same thing? Yeah, so a lot of algebra on that one, but nothing you shouldn't be able to handle. So when we have all even powers, you go jump into the half angle formula. That was the strategy. Just keep expanding. Here we ended up in one of those previous situations where we had an odd power, in which case you just save a factor for cosine and change everyone else. Maybe someone else tell me how to deal with the cosine cube blah blah blah. Tell me about the last one. Yes.
I think it's I was like, because there's an elevator
Yeah,
problem.
don't worry about it. Just sit down.
So I saw you earlier, so you should have.
Yes, I know. Just sit
Yeah.
down. Just sit down. It's okay. What do you want to do here?
So you can top,
Huh?
you can get cosine 2x times cosine x.
Okay.
And you can change the cosine 2x to 1 minus sine squared x cosine x. And then you can do a u substitution for the denominator. So
Okay. So we set u squared equals sine x. Right. So you say u equals the square root of sine x, which means that u squared is equal to sine x. Do u squared substitution. 2 du is equal to cosine x dx. And so this guy is going to become, well, underneath I'm just going to have u cosine x dx. This part here is going to be 2u du. And sine squared is going to be u to the 4th. So this is 1 minus u to the 4th. And that's everyone. Just cancel. That's just u minus u to the 5th over 5. And our u is the square root of sine. So that's that one. Okay. So yeah, turns out we could learn by osmosis. So if you kind of play the same kind of trick, split things up how you wanted to take advantage of your trig identities to get into a situation where you can maybe do a convenient use of them. And that's fine. We are going to deal with the second kind of integral that we mentioned, the type of product of secants and tangents. And remember, we're skipping the cosecants and cotangents. Pretty much the strategies that work here will work there as well, where the cosecant will kind of play the same role as the secant, and the cotangent will kind of play the same role as the cotangent. They have very similar Pythagorean identities connecting them. So teaching about secants and tangents, I'm also teaching about cosecants and cotangents. Pretty much the same sort of strategies. This form has 3 cases. So, case 1 would be m even especially tangent present. Case 2 is n is odd and secant is present. Or you can actually force it to be present through identities. And case 3, believe it or not, everything else. So the power of secant is even and the power of tangent is odd. We have 2 nice methods for those, and then I'm going to tell you how to deal with every other situation all at once. So the first 2, pretty much going to get through those quickly.
But can you read back case 1?
Yeah, what's in case 1 say?
Yes, especially.
Oh, okay.
This is ESP, so, which I know is an abbreviation for something else, but I meant it for especially. Let's look at case 1. So here's what you're going to do in case 1. In the case that you have an even power of secant, of course it would be greater than or equal to 2 actually here, because the point is you want to, step 1, save a factor of secant squared. Change any remaining secants to tangents. 3. Of course, you're going to use the identity 1 plus tangent squared equals secant squared. And step 3, you're going to substitute. For the tangent, your du is going to be that secant squared that you had saved, or of course you just integrate. At this point, it should be something that you can actually break up into something where you can use the power rule. Integrate. So let's do some examples of this case. So once you see the power of secant is even, bigger than 2, just break off the secant squared. Greater than or equal to 2. Break off secant squared, change everyone else to tangents, do a substitution for tangent. Let's consider this case. Okay, go. What do you think?
So separate it into secant squared times secant squared df. And then use the identity secant squared minus 1 equal to tangent squared. So you would have tangent squared, or hold on.
Yeah?
You separate the secant squared, I do one plus tangent squared. Now you make transfer tan x to u, because the derivative of that is
Right.
squared.
So you save a factor of secant squared, just factor it off and have them sit there. Any other secants around, change them to tangents using the identity that I mentioned here. and then u equals tangent. Your d is going to be that secant squared x dx, and so this integral is going to become pretty much 1 plus u squared du. That's that one. Questions on that?
Don't erase this, I'm trying to copy this down. Okay.
Start working on the next one. Could have made this one even a little more interesting, like tangent to the 10th power or something. Wouldn't- Which is not going to be that bad. Like the power of tangent doesn't even matter here. Step 1.
Say the secant squared.
This guy changed. Equals tangent. du equals secant squared. So this just becomes 1 plus u squared times u squared du. So notice I could have put any power for tangent here, it wouldn't really matter. Even u to the 10th here is not going to pose a big problem. Of course, probably catch some students freaking, oh my god, it's the 10th power. They just freak out because they see big numbers. You guys are different. You guys are my students. You don't freak out. Leave that for the other people. Leave that for the normal people. No freak out. A lot of times students make mistakes because they freak out. Oh my god, there's a radical. Just square everything. And they panic and they do stuff they're not supposed to be doing. Like, don't panic. See a secant tangent, secant to the 10th. I could have put secant to the 100. It shouldn't matter to you. Like, oh, there's a strategy for this. I know how to do it. Everything's fine. Everything is under control. Expand here, you're going to have a u squared plus u to the 4th. So, case 1 not so bad, as long as you can say the secant squared, change everyone else. And of course, we do remember that the integral of secant squared by itself is just tangent, so even if there's a secant squared by itself, doesn't really matter. What formula for that? Case 2. So for case 2, you need to have the secant around. It almost doesn't matter what the power is as long as it's present, as long as the power of the secant isn't like 0. So what you're going to do. So this is when your power of tangent is odd and there's like a secant somewhere right there. What you can do is save a factor of secant tangent. modify this identity to change all the other tangents. We're going to do a substitution for the secant this time. Of course, that should be put you in a nice position to just integrate. It should look like a polynomial maybe, or at least something else where you can simplify to use the power rule at this level. Examples. Yeah.
You can send the tan in terms of secant. So you can square x minus. You split the tan into tan squared x and tan x. Now take the tan squared x and turn it into the secant squared x minus x.
Secant squared minus 1 would give us the tangent squared.
Now you can make u equal to secant squared x and secant x. And
Save a factor of the secant tangent over here. And so now u equals secant. Your du is going to be that secant tangent. Yes.
So we would get, so for the secant, right?
Mhm.
Secant squared minus 1 times secant plus times tangent, right?
Yes.
We need to replace the secant with the u. So I guess the u can be the secant, you know, and if you replace it with u and, you know, u times, you know, u squared plus 1, you would get u cubed plus u, and if you were to take the antiderivative of it, it would be 1 over 4 u to the 4th power plus half u squared. And you would get, if you try to replace u with secant, you would get 1 out of 4, parentheses secant.
I think you're moving ahead of yourself. So you're talking about the next step, and I think you're miscounting something. Because
But what you would get is that 1 out of 4 times, you know, 1 out of 4 parentheses secant.
yeah, you're talking about the next step.
Power.
So
plus
we're about
half
to do that.
Parentheses secant x squared plus c.
So with the u and the du, as you said, this is going to look like u squared minus 1 du. So there should be no 1 over 4 anywhere. Yeah, there's no 1 over 4 anywhere. U is secant. The derivative of secant is secant times tangent. So this whole thing gets rid of, we get rid of that by the du. So you end up with u squared minus 1. I think you multiplied out a secant to get a secant cube, which you shouldn't. It's not a part of the strategy. So that's going to be u cubed over 3 minus u plus c. And our u was the secant. So that's that. Moving on. What do we do here?
Same strat, just to get secant.
What are you going to say?
So that'll be secant squared times tan squared times secant.
Alright, save a factor of secant tangent.
And then convert the tan squared to secant squared minus 1. U equals secant.
And u equals secant. Secant x tangent x. And at some point, this gets all very boring, as some of you are probably realizing. But that's good. So, as I was telling my other class, that's how you know you've studied enough.
Where it gets bored.
When it gets boring, when you're getting things right and you're like bored, oh god, I have to do like 5 more problems. Come on, I got it already. Students often prematurely stop studying. You know, they're like they're struggling, they're trying to get stuff right, and they're practicing wrong, and they oh my god. Okay, and they have to look up stuff, and they have to look on Google, and they say, what did you want to do again? And look back at their notes, and they're struggling, and they keep getting it wrong, and they're working hard, and they're there for hours, and finally they get to a point where they got one right, and they're like, yes, oh my god, and they're so happy, and they're so relieved, like, ah, I think I got it now, and then they stop studying.
Nah.
No. That's how you go into a test thinking, I think I'm going to do fine, and then when the test comes up, Professor, I really understand the material. I got the problems right. I've been studying for like 3 hours. No, that's you stop too early. Right? Like literally what you just practiced is getting it wrong 95% of the time. And then you got it right 5% of the time, and you pat yourself on the back about that. Like you're practicing failing and thinking somehow that that's going to bring you success. No, that's not how you get success. When you're getting 90% of things right, and you're literally just bored, right? Like you just see what to do. Your mind is already skipping 2 steps ahead of where you're writing down. That's when you know you're ready. When you're at that point, even if I throw a curveball on the test, which I usually don't, it's not actually going to matter. You're going to be like calculus ninja. So now this here is u to the 4th minus u squared du, u to the 5th over 5, u cubed over 3. And use our secant. Secant to the 5th over 5 minus secant cubed over 3 plus. Now case 3 is a little bit more interesting. You find yourself in case 3, you probably won't get bored as quickly. So here are the steps for case 3. Okay? So if you're not in the case where you can save an even power of secant, or you can save a factor of secant tangent and change all the other guys to secants, you find yourself in case 3. So here's what you can do in case 3. So step 1. You're going to try something. Hope it works. 3. If not, try something else.
It's just brute forcing.
So this is the case where you start to realize, we're not in Calc 1 anymore, are we? That is right, children. The world is more complicated than to fit into a set of strategies all the time. So at this point, hopefully, you're very good at the formulas, you're very good at your trig identities, so you can kind of see connections where the untrained eye might not see them. Try something, figure it out, and you'll even, in this case, just know some certain cases where it seems like, okay, statistically speaking, if I try this out in this case, chances are it's going to work out. But there are no guarantees. There's like no standard set of strategies that can deal with this. Let's actually do some examples of case 3. Integrate tangent cubed.
So
F. Integrate secant cubed. integrate secant x tangent squared x. Okay, who wants to try some? Yes. Yeah?
So you have tan squared and tan. And then you make tan squared into secant squared minus 1.
Yeah?
You make u equals secant.
If u equals secant, your du is going to be secant tangent. You only have a tangent. Yeah?
How many you distribute because then you can at least solve one part of it. Now this way you can make u equal to secant x the first part, and then du will be like separate the thing.
Yeah, at this point, you can make u equals secant, and you'd have the secant tangent there to be the du. You could also make u equals tangent, and then the secant squared is your du. At this point, you kind of have options. Let's go with u equals tangent. My du is going to be the secant squared. So this is really just going to be the integral of u du minus integral of tangent.
ln of the absolute value of secant.
Right, that's something you guys should have memorized. It's one of our basic rules. And of course, that's going to give us the u squared over 2 minus the ln of secant. And our u in this case was tangent. Tan squared over 2. Now you're like, that wasn't so bad. Got me all scared with this whole thing. Was it just a gimmick? You have a question?
Is there also work if I put for the tangent to x, if I put like sine and over cosine, and then I set equal to the u equal to
If you had like a sine cubed over cosine cubed,
yeah,
and then do what?
and if I do u equal to the cosine, and the du will be sine, and then solve it, am I gonna get the same answer as this?
So you would have, essentially that would become 1 minus u squared over u cubed. Negative, right?
Mm-hmm.
And so that would be minus the integral of u to the minus 3 minus, well, 1 over u du. So yeah, that could also work. And so that would just be ln of u and minus, add 1 to the power, divide by the new power. Plus c. So that could work. Yeah, where your u in this case is cosine. Yep, so that's also valid. The suggestion here was a u equals cosine x substitution. You'll get this after you plug everyone in. Yeah, so that's another way to do it. Which, of course, the answer here is going to look different from what I got here, but maybe, from what I got here, but maybe you would, maybe I'll leave it to you guys to tell me why it's actually okay. Maybe next time. Because it turns out for trig integrals, you sometimes can have different looking answers, but they're all actually valid. Just something to keep in mind. Just add another layer of complication in every day. Yes?
Where did the ln secant x come from?
The integral of tangent is ln of secant
Oh,
of the absolute values. That was one of our basic rules. We derived that, was it last class or the class before? It's one of our basic rules.
This one. So this is expressed.
Okay. What about the integral of secant cubed?
okay, I
Yes,
see.
it's two different ways.
Ideas? Yeah.
I guess you could approach it the same way, like split up secant squared,
Makes sense.
and then secant squared is going to 1 plus secant squared. Distribute it. And then now you could be secant.
But where? Here?
Yeah, or like that.
If you use secant, your d is going to be secant tangent. You're going to have a tangent left over, which that's going to throw in a whole radical thing into it. So probably not where you want to go. Other ideas? So this one we actually know.
Oh, could you take out a secant and tan x, like secant times tan x?
Okay, and you'd be left over with a tan x.
Yeah.
And what are you going to do with that?
So
Yeah?
Well, the integral of secant x is ln with the absolute value of secant x plus tan of x.
Yep, we looked at that last time, and
And for the second one, I would like take out the tan x and then set in equal to tan x. And take the derivative of that. So we get
so you want to think of this as tan x times secant x. And you're going to say u equals tan x. Your du is going to be?
oh,
Other ideas?
I guess, like, you know, trying to see secant squared x minus 1 times secant.
Okay, trying to apply an identity here. Tangent squared is secant squared minus 1 times secant. And what's going to happen here? So this is going to be the ln of secant x plus tangent x plus, I guess we can distribute the integral of secant cubed minus the integral of secant x dx, which is actually the same thing here. So that guy cancels out. And we arrive at the conclusion that the integral of secant cubed is the integral of secant cubed. Welcome to case 3, right? Something that made total sense in the, yeah, why wouldn't this strategy work? It works so nicely right here, didn't it? Doesn't work again. We have to be a little bit more creative. The same strategy isn't going to work twice. The same strategy is not going to work in all cases. That's the nuances of case 3. So yeah, other ideas. The same strategy is not going to work. The strategy here is actually radically different. No pun intended, done. It doesn't involve radicals. Ideas.
don't know where I would go after this,
Okay.
but 1 over cosine cubed. X. And I don't know if we could use like one of the type 1 strategies to do that, or I don't know, that's
Okay, so how is that gonna work?
You gotta give me a minute. Okay.
You have an idea how to continue with this?
So can we pull out a cosine squared and a cosine, and then use the identity for cosine to get, what was it?
1 minus sine.
1 minus sine squared? And then let sine equals u.
And then,
Sine equals u, derivative of cosine, yes.
at this point, what would you do?
Yeah. Could we do
No,
u
yeah, I
subs?
think that would work.
Could we do a u substitution for sine?
U equals sine, what would your du be?
Oh, no, yeah, okay. Never mind.
How do I apply that here?
Yeah, never mind.
Because that cosine is in the denominator.
Right.
What if we multiply and divide by cosine? Right? That's a math trick that seems to work all over the place. Right? So we can get that here, so this would actually be 1 over 1 minus u squared squared. Du. Do you know how to do with that? There are ways you could deal with this with a hyperbolic. The other more straightforward way to deal with an integral like this would be using a technique that I haven't taught you yet. That's like 2 sections away. So at this point, this strategy is sort of out of reach. And I'm actually not as convinced that it would actually pan out in the end. We would sort of end up with like a similar thing happening. I'll give you a hint. Integration by parts is the go-to technique here. So now that I told you, like, we're out of nowhere, right? Integration by parts, what do you think? Who would have thought? Integration by parts would be the nice first step here. How do I get it to work? Yeah?
Separating between square x and you can then square x and secant x.
And you're going to choose your u and your dv, which, notice in this case, Liate is no help whatsoever, right? So that's the first thing that's really weird about this, but let's you want your u to be what? 1. And your dv to be the secant squared. So your du is going to be secant x tangent x. Your v is going to be, well, tangent. And so you're going to plug this in u times v minus the integral of v du. Where do you go from there? Ideas at this point? The formula, it's v du. So tangent times the tangent is tangent squared. What do I do with that?
Isn't that another case 3? Like it's just, we gotta, is m, is odd.
Yeah, it's another
It's
case
just
here.
another-
So what do you want to try? Just try some, yeah.
I would do tan squared x equals secant squared x minus 1.
Okay.
And then if you distribute it out,
That will be an integral of secant cubed.
x minus
Well, the plus the integral of, what's so funny?
Because you get the secant
Oh,
cube again.
But you can set it equal to secant cubed of x and then add.
Don't laugh, that's actually a lot better than the last time. There's a negative sign in front here. What does that mean? You can add it to the other side. And it's not going to be something silly like 0 equals 0. So I can add this guy to the other side. I'm going to have 2 secant cubed. Plus the integral of secant. What's the integral of secant?
ln secant x plus tan x.
Of absolute value, secant x plus tan x. This is secant x tan x. And if I want to solve for this integral, I'm just going to divide both sides by 2. Not plus b, plus c. And that's it. That's the correct answer. Right, totally different strategy than the first time. Unfortunately for case 3, there is no general strategy. There are things you can prove using case 3, like reduction formulas and things of that sort. It's probably not in your online homework, but I think your textbook should have some examples where it has you derive these convenient formulas that might help out. But that's it, yeah.
How'd you get the 2 outside the integral?
I added, I have a minus secant cubed, add secant cubed to both sides. And yeah, so that was weird. You want to know something even stranger?
Yes.
This is now a basic formula of ours. Now, I know it sounds a little bit crazy, but it turns out this integral actually pops up all over the place, the integral of secant cubed. Something you should know off the top of your head. You don't want to have to do this all the time. He's going to pop up when you least expect it, trust me. It's one of those things, one of those peculiarities. Sometimes you have E and pi pops up out of nowhere, like why is E and pi here? I don't know. But yeah, secant cubed shows up all the time when you're like doing integrals. Hey, what's up? Like he just pops up. At this point, I want you to have this memorized. Let's move on to 2. Okay, ideas.
Didn't we just do this? We're trying to figure out secant cubed.
Yeah. Yeah. This was a part of it. So what do you want to try then?
So you turn tan squared into 1 minus secant squared.
Well, into secant squared
Yeah, secant squared.
minus 1. It's going to pretty much be secant cubed x dx minus the integral of secant.
And now we have 2 basic rules.
Ah, now there's the 2 basic rules. Secant cubed, we know that. That's 1/2 secant x tangent x plus ln secant x plus tangent x minus secant x plus tangent x plus c. And so we have a half of this minus that. You could even write this a little simpler. 1/2 secant x tangent x minus ln secant x plus tangent x plus c parentheses here, parentheses. That's all. case 3, do a lot of practice to be comfortable with something like case 3. Eventually, you'll start to see it, you know, like Sasuke opening a Sharingan or something. I see it now. Okay. You go down and okay, I got this. All right. But yeah, it's going to take a lot of practice. There is no general rule I can give you, unfortunately. Sometimes, like out of nowhere, integration by parts. Hey, it seems to work out. Sometimes just applying your trig identities finishes everything. It's kind of a toss-up. There's no way to actually give you a general method here. But that's case 3 for the secants and tangents. And like I said, cosecants and cotangents, very similar to this case here. But yeah, with that, let's move on. We're going to look at another topic now. I believe this is 8.4. We're going to learn about trig substitution. Trigonometric. But no one says the metric part. Substitution. So, we've all seen the idea of sometimes doing a substitution in a very weird way, like instead of doing a u substitution, do a u squared substitution or something like that. This takes that idea and really runs with it. We are going to find ourselves in a situation where somehow putting in a trig function is going to make our lives easier, as weird as that might sound. So here's where the idea comes from. We know about some nice identities like Pythagorean identities. So for example, we know that 1 minus sine squared is equal to cosine squared. And we know that 1 plus tangent squared is equal to secant squared. We also know that, say, secant squared minus 1 is equal to tangent squared. And here's what I'm going to do. I'm going to multiply both sides by a squared. Why would you do that? We'll see. Multiply this by a squared. Notice that I can write the right side as a squared minus a sine theta. Maybe it's nice if you use theta. It's not really going to matter, but I don't want people to get confused. For aesthetic reasons, it's nice to understand. That's going to give me a squared cosine squared. And here, if I multiply both sides by a squared, notice that this looks like a tangent theta squared. That will give me a squared secant squared. And here, if I multiply both sides by a squared, I would have a secant theta squared minus a squared equals a squared tangent squared. So far, not very mind-boggling, like, okay, I see what you're doing, but why do we care? Here's the nice thing. Notice on the left side, I have 2 terms. On the right side, I have 1 term. Are there situations where we prefer to have 1 term as opposed to 2 terms? Sure, lots of situations. For example, if this were under a radical, would be a situation where we prefer to have 1 term under a radical than 2 terms, right? This part is very nice. That part, we don't really know how to do it. Yes?
Sorry, on the last problem,
Oh,
where did the second ln secant x plus tan x go?
Yes. What?
The second one, where did it go? Because it says minus ln secant.
Well, this one is 1/2, because the half multiplies out.
Mm-hmm.
And then minus this one. Right? So I have 1/2 of this minus that, I get minus 1/2 of that. Right? Half an apple minus an apple is minus half an apple. And so I have minus the half of this. I just factored out the half again. Okay. So there are situations where, instead of having these 2 terms, I'd rather have 1 term. And we're going to see where that's convenient in a little bit. But here's where it gets really ingenious. Let's think of this guy as just some variable, like x. Let's think of this guy as some variable. Let's think of this guy as some variable. And basically what am I saying? I am saying that somehow now we have an equivalence between, if I see an expression like a squared minus x squared, if I think of the x as a sine function, it will allow me to simplify this into an expression that looks like that. And if I somehow equivalent, it's not exactly the same thing, of course. And if I see a squared plus x squared, somehow there's an equivalence in my mind here with a secant squared. And if I see x squared minus a squared, there's an equivalence here between the tangent squared. Now, let's put this all together. You could write this out, it's not really important, but I just wanted to, I'm going to give you a table. I just want you to have some idea of where the table came from. It kind of came from this. Us knowing the Pythagorean identity, generalizing the Pythagorean identity, and saying, hey, if I just think of this as some variable, it kind of looks like one of these expressions, and somehow I've made it equivalent to these trig functions over here. So here's how we're going to actually make this idea useful. These expressions are now going to be very important to us. So we can create a table with a certain expression. One possible expression is going to be like the a squared minus x squared. Another possible one is going to be the a squared plus x squared. And another one is going to be the x squared minus a squared. So these three expressions are going to be very dear and near to us right now. They are going to be things that your eyes should be tweaked in looking for. Like the difference and the sum of squares, where one part is a constant and the other part is a variable. So these are the important expressions. Now, it turns out, whenever you see that expression, it may be the case that a very convenient substitution will be in play. Namely, the substitution, let the x look like a sine function. You would substitute x equals a sine theta. In here, let the x behave like a tangent. Substitute a tangent theta. And in this case, let the x behave like a secant. Substitute x equals a secant theta. Okay. Now, once you actually do these substitutions, certain things become useful. Useful facts, I guess. And again here, not very groundbreaking. Basically, if our x is a secant sine theta, this means that sine theta is going to be x over a, which means I'd be able to draw a triangle where this is opposite over hypotenuse, and this is going to be the a squared minus x squared. And notice from this I can construct all other trig functions and find other trig functions. Similarly here, if my tangent theta is x over a, this leads to a triangle. Tangent I know is opposite over adjacent. So this is going to be a squared plus x squared. And I can use that to talk about the other trig functions. Here, if my secant is x over a, this leads to a triangle where secant is hypotenuse over adjacent. So this is going to be x squared minus a squared over here by Pythagoras' theorem. So I made this substitution because it reminds me of 1 minus sine squared that I can collapse into a cosine squared. This reminds me of 1 plus tangent squared that I can collapse into a secant squared. This reminds me of secant squared minus 1 that I can collapse into a tangent squared. And at the moment, very innocent looking table. How useful could it possibly be? Let's see. Let's actually just jump into some examples so you can see how useful this table is going to be. See firsthand. space in my hand. Give you guys some time to copy that, and we're gonna kill all those integers. They're all dead and walking. I'm not gonna get through all of them, but whatever we don't finish, you guys do them over the weekend. Yep. Yes, minus 4x. So it's the 1 over the square root of negative x squared minus 4x. We all have this too. So, you see this integral pops up. What do you think? Yeah?
For x, can you substitute 16 cosine squared theta, because that's not the solution. It's a squared minus x squared.
How would you get that?
Under the radical it said 4 minus x squared.
Mm-hmm.
So we think a is equal to 4, and then
No?
no.
You would set A is 2, and you would set x
A is 2 in this case, because that is 2 squared minus x squared. Okay, so but in general, the first thing you're going to think, and the first thing you always think, is that a basic rule? No. Can it simplify it? No. Can a substitution work? What does substitution work on this one? Like a regular substitution. Why? What's the problem? What would you have substituted if you wanted to do a substitution? Right, u equals this. Your du would give you what? Like a minus 2x, right? But you'll get an x out of it. But you'd have an extra x left over. What are you going to do with that? That's going to be some complicated radical. You're not going to end up in a better situation, right? So the regular old-fashioned substitution that you learned from Calc 1 is not going to be a very useful thing here. So now you start to notice that, but that should cross your mind first. Could a substitution work here, right? Now, when you realize that that doesn't work, now you start looking for some other way to grapple with this, and that's when you're going to notice, hey, 4 minus x squared. That's like 2 terms. I can think of that as a difference of squares, and that looks like an a squared minus an x squared. And I kind of know that reminds me of something. At this point, you are going to do a trig substitution, which would be the correct one here. X equals
2 sine theta.
2 sine theta. Okay, so we're going to jump in with that. Dx would be 2 cosine theta d theta. And so now what we're going to do is we're going to go here. We're going to plug in all these trig functions. So this will be the integral of x squared is on top. X is 2 sine theta, so that's a 4 sine squared. Underneath, I have the radical of 4 minus x squared, but x squared is 4 sine squared. The dx is 2 cosine theta d theta. Now, at first this kind of starts looking even scarier, but then you realize, hey, there's a trig identity here. I can collapse that into an a squared cosine squared, right? So I can factor out the 4, I'd have 1 minus sine squared, which is cosine squared. So this all reduces into the square root of 4 cosine squared. And I can take the radical of that, that's a single term. So what ends up happening here, I have 4 sine squared times 2 cosine theta over, that now becomes 2 cosine theta. This cancels that. So now this integral reduces to that trig integral. And we caught a lucky break, because you're all experts at trig integrals now, right? How would you integrate this guy? Yeah?
We use the double angle one?
Double angle formula. That is a case for the sine cosine variation. You see an even power of sine and cosine, you apply the double angle formula. So that's going to look like 2, 1 minus cosine 2 theta, d theta. And so that's going to be 2 integral of 1. No.
3 theta.
Theta. D theta. Integral of cosine 2 theta? 1/2 sine 2 theta. And that's the answer. That's the integral. Problem though, you never leave your answer in the substituted variable. You always want to change it back to the original variable. How do we get this back to x's?
you have to solve the theta for the x. Like you divide-
Right, so I can solve for theta here.
Yeah.
My theta is going to be the sine inverse of x over 2. What about this guy?
That's just x. 1/2 x. Right?
That's not x. X is 2
equal
sine
to
theta.
2 sine theta. Oh, sine 2 theta.
This is sine of 2 theta. How do I change that guy? Ideas? So yes, the theta is going to be that, this is going to be the sine inverse of x over 2. We know that part. This part, how do I change that to x's? Ideas?
Can't you just plug in the theta with the same thing?
So you want to find sine of 2 sine inverse of x over 2?
You draw the triangle like you drew before and set your values.
Right. At this point, I'll direct your attention to the third column of the table I gave you guys. Hey, these might be useful. Being able to set up a triangle. I can figure out any other trig functions based on that triangle. So what I would do here is I would go set up that triangle. Now, notice here my sine theta is x over 2. That is opposite over hypotenuse, which means this is going to be 4 minus x squared, which means I can figure out what cosine theta is, for example. Cosine theta is going to be adjacent over hypotenuse. So my sine theta is x over 2, my cosine theta is that. Can we figure out this guy? Yeah.
You can use 2 sine theta. cosine.
That's a double angle formula, also for double angle formula for sine. That's 2 sine theta cosine theta times a half. So this part is just sine theta cosine theta. But I know what sine theta and cosine theta are from this useful little triangle over here. So that gives me the answer at this point. So that is going to be sine inverse of x over 2 minus sine theta times cosine theta. That's that into it. Don't worry, a lot of you might be feeling a little weird about this and feel a little shaky here. There's a reason we have so many examples. Okay? We're going to get through this, don't worry.
Wait, wouldn't that be x over 4? And then also.
Well, you could put it at, you could take the 2 times 2 and put it over 4. Same thing, no different. So that's the first one. Let's do the second one. The second one's a little less scary. In fact, for the second one, you should already know what the answer is. What is the answer? Integral of this. Tan inverse of x plus c. Okay, so we already know the answer. So suppose hell freezes over and for a second you forget that formula, which don't forget that formula. But let's say we're in an alternate universe and your doppelganger forgot that formula. It turns out with the techniques that I just told you, your doppelganger would be able to actually figure out what that is. So based on the technique, the table that I told you, how can you actually apply that here? Give me a guess, the wrong one. What do you notice?
A squared plus x squared.
It's an a squared plus x squared, because it's 1 squared plus x squared, which means your a is 1 in this case, which means, what would you set x to? 1 tangent. Your dx would be secant squared d theta. We go and we plug that in. This would be 1 over 1 plus tangent squared times dx, which is secant squared. How do we do that integral? one of those secant tangent ones.
Can we choose the secant square for our tangent?
How? What would that be?
That one says secant square minus. No.
Yeah.
It'd be secant squared, you can substitute 1 plus tan squared to it.
Right. Or 1 plus tan squared can substitute for secant squared. Probably nice one to do here. They both end up doing the same thing. Just cancel. So this is actually going to be the integral of 1 d theta. What is the integral of 1 d theta? Theta. What is theta? Well, if x is tan theta, then theta is going to be tan inverse. That's the answer. Figured out that that was tan inverse with the power of a trigonometric substitution. Not that we'd ever forget, but I expect this to be a little uncomfortable, so I thought you'd like to see a familiar face. You know, when people see a familiar face, they calm down a little bit. I'm so glad to see you here, man. Like, things are getting scarier around here. Okay. Okay, let's jump back into the scary stuff. Maybe now you're a little bit more comfortable with the ideas. See that. Now, of course, the first thing I'm going to think, can I simplify to use a basic rule? Can a substitution work out here? It's not going to work out. Actually, a substitution could work out here, but that's going to put you into a situation where you need to use a technique that I haven't taught you yet. The same technique that I alluded to earlier in the class when I said, hey, you need a technique that I haven't taught you yet. It's the same guy, actually. So technically, you could get a substitution to work here, but you'll go into a situation where we don't know how to deal with it yet. So substitution doesn't work. So what we're going to try to do is a trig sub, because at this point you should notice a very auspicious expression, x squared minus 3, which means that's a difference here where the x is squared. How can I think about that? How do I take advantage of that x squared minus 3?
You just have to do a is radical 3.
A is radical 3, right? So the 3 is radical 3 squared. So that looks like x squared minus a squared, where your a is radical 3. So what would you set x to be?
Radical 3 secant.
Radical 3 secant. This would give us, this would mean that our dx is going to be secant tangent. And now we go and we plug this all into the integral. So I have 1 over x squared. X is this, that squared is 3 secant squared theta, the radical. If I plug that in here, this is going to give me 3 secant squared theta minus 3. And my dx is going to be radical 3 secant theta tan theta. Now at this point, you'll realize that this here, this is 3 secant squared theta. This here is going to be radical 3 tangent theta, right? Because secant squared minus 1 is tangent squared. Times radical 3 secant theta tan theta. How do you deal with that guy? Yeah,
Can we pull out a secant tan on the bottom?
sure. And what would you do with it?
And then could you do like a substitution? U equals secant, du secant tangent.
You're thinking too complicated.
Oh.
Did you cancel?
Just cancel.
Just either one.
Like secant cancels one, the secant tangent cancels tangent. The radical 3 cancels the radical 3. Like we're all in calculus mode. Don't forget algebra just because you're in calculus mode. Okay. can cancel that to simplify it. So ultimately, this also, we're continuing over here. This is going to be 1/3 1 over secant. How do you deal with 1 over secant? It's cosine. How do you deal with integral of cosine? That's just sine. How do I get that back to x's? Do that triangle thing. I know that my secant theta is x over radical 3. Secant is hypotenuse over adjacent, which means that this is going to be the square root of x squared minus 3. So if I wanted to find my sine of theta from this, that's opposite over hypotenuse. So come here and plug that in. So this is the square root of x squared minus 3 all over 3x. That's that into. Another example. Ideas.
Is this like a completing square?
Complete the square seems like a good idea to me. How do you complete the square?
Oh my god. Completed the square.
Gonna tag someone in. You know how to complete the square, Jhevon. Yes, I know. Can someone tell me how to do it here?
Take half of the middle term and
So it's x plus 2 all squared. How do I figure out what's left over?
I guess
Yeah.
it'd be x, x plus 2 squared plus 4.
Plus 4. If I were to multiply this out, I would get a plus 4, and then plus 4 to get back to the plus 8. So that is completing the square. Okay, so we complete the square. That gets me into a situation where I have two terms, where one of them, the variable part is squared. How can I take advantage of that? Yeah, 4 is equal to 2 squared. So that's the a, your a is 2, so what are you going to do here? X plus 2 equals?
210.
210. So my dx is going to be 2 secant squared theta d theta, and I'm going to plug that all in. So this would be the radical of 4 secant squared theta is 4 times my dx is 2 secant squared theta d theta. And of course, this guy here is just 4 times tangent squared, so that all simplifies to 2 tangent theta. And on top we have 2 secant squared theta d theta. But this is a tangent. My mind was skipping ahead to the secant part. So that's actually 2 secant. my x plus 2 is 2 tangent theta. So x plus 2 squared is 4 tangent theta squared plus the 4 from here. Can factor out the 4, I get tangent squared plus 1, which is secant squared. Then I take the radical, and that's 2 secant theta. 2's cancel, secants cancel. We end up with the integral of secant theta. How do we integrate secant theta? Like, Devin always comes in and says, oh, like this is one thing you're not going to get wrong on any quiz. Like you've repeated it so often. All right, how do we get this back to x's? The triangle. So we know that tangent theta is equal to x plus 2 all over 2. Tangent is opposite over adjacent. That's going to be this squared plus that squared, which knows x squared plus 4x plus 8. So our secant theta from this, secant is hypotenuse over adjacent. Tangent is, well, it's x plus 2 over 2. So I'm just going to plug these guys in. This is ln of the square root of x squared plus 4x plus 8 over 2 plus x plus 2 over 2 plus c. Now, that's the answer. However, if this were a problem from the textbook would actually write the answer as this. Why is that acceptable? So you got to this as the answer, flip to the back of the textbook, you see this. Man, where did I go wrong?
Oh, because you can combine, it's all, both those terms over 2, and then you
Yeah.
can subtract the logarithm, or ln of 2, which is just 0.
Right, so at this point, log of a over b, you should remember it is ln a minus ln b. In this case, your b would be 2, which is just another constant, so you absorb it into that plus c. So rather than writing ln of a fraction, the textbook would rather typeface this, typically put everything in one line, and so that would be wait till you guys finish copying so I can start numbering. I feel we're going from that panel to this panel. Just want to go from left to right. We're going to tackle this next. So if you already had everything copied, try to figure out what you would do here. I'll give everyone else another 20 seconds, 30 seconds. Okay, so that table I gave you at the beginning of this section, obviously that's another thing you have to have memorized, because you need to know what expression is convenient for a trig substitution. So the main trig substitution is x equals a sine theta, or x equals a tan theta, or x equals a secant theta. Technically an a cosine theta can work in the situation where you have a sine theta, but it's more traditional to use the sine version. But you should know when you can actually substitute these expressions and get something useful. Ideas? Yeah.
So your a is your 1, and your x would be 2x. So if you like set 2x is equal to tan.
So 2 dx would be
2 dx would be secant squared.
in other words, my dx is going to be 1/2 secant squared. We go in here, I'm going to plug that in. So that's going to be 1/2 secant squared. That gets rid of my dx part. This part is going to be the radical of, well, tan squared plus 1. Which of course is secant squared, and I'm taking the radical of secant squared, so that's going to be secant squared over secant. Which is integral of secant. What's the integral of secant? Jhevon, you're sleeping. Made him get it. How do I change that back to x's? Triangle. So obviously you guys are building up some strategy in your mind for this. You get your useful expression, chain it to a trig function, use the rules that I taught you in 8.3 to solve that integral. When you want to get back to the original variable, triangle. So the triangle in this case is tangent theta is equal to 2x. Of course, think of this as 2x over 1. That's opposite over adjacent. This would be the sum of the squares square rooted by Pythagoras' theorem. Therefore, I can say my secant is going to be hypotenuse over adjacent. And my tangent, well, my tangent is 2x, as you know. So I go here and I plug those in. ln of square root of 4x squared plus 1 plus tangent 2x plus c. And we're going to stop at this point. I'd like you guys to complete the rest for next week. Because next Tuesday we'll be on everything up to trig substitution. So getting good practice from this. And I'll probably post the homework as well so you can get even more practice. Get used to doing trig sub. It's useful in such situations where you might not be able to get a regular substitution to work. You will pick up with that on Tuesday.